Hello, welcome to Engineering Design and Practice CAD part of the module. So this is the second session recording. In the first session, we made an introduction to CAD and SolidWorks. So we discussed the basics of sketching and part modeling techniques. So in today's session, we are going to be covering more advanced part modeling techniques. We will also talk about design intent and how we can use different part planning steps when we are making parts in SolidWorks. Today's learning objectives, so hopefully by end of this session, you will all have knowledge on how to create planes or different reference geometries on SolidWorks. We will be discussing the swept boss base features, and we'll discuss how this feature can be used to create springs or machine threads. We'll also talk about cosmetic thread, how we can simply represent thread geometries in 3D environment using a simple method. Then we will discuss two other advanced features, loft and shell. Then we will show different reference features other than planes. So we will talk about how to create axis and point, and then we will use hole wizard feature, and then we will show you how to plan complex part, what steps you need to follow, which may help you to design fairly complex parts in SolidWorks or in any other CAD package. And finally, we will discuss how you can find out different mass properties, how you can apply material to your parts. So hopefully by completing this session, at the end you will have all the skills required to complete all parts for your Stirling engine assignment. So your Stirling engine assignment, that would be 15% of your final module grade. So hopefully you will have all the skills to make the parts before we start discussing about the assembly techniques in the next session. So here is an example of the parts of the Stirling engine. So let's briefly discuss about what you need to do for this exercise. So effectively, as we said earlier, you'll have to create all the parts that make up the Stirling engine, and then you need to put all parts together to create an assembly, and then you'll have to create drawings for some of the parts. So there are 5 key components would be listed on the assignment brief. So those components are also included in your own Flywheel design. Then you'll create an assembly drawing of the complete assembly model and produce a photorealistic rendering of your complete model. So when it comes to assessment, you'll basically be assessed on the accuracy of your 3D parts and assembly. elegance of your part design. So basically how you structured your parts, how you use design intent, how you made your sketches fully defined, or models are easily be modified if that's required. So you should pay attention how you modeled your parts. And the most important bit is the quality of your drawings. So we will discuss different drawing rules according to British standard. As we briefly mentioned in the first session, we will be using BAS 8888 drawing standard from British Standards Library. So the quality of drawings are going to be one of the key bits in your assessment. Okay, let's get started with some advanced features. So the first one we will be discussing today is plane feature. So if you recall from the first session, we said that every SolidWorks part comes with three main planes, top, front, and right planes in the design tree. So we could use those planes for sketching. We also said that if we have any existing planar geometry, so we can use planar faces. So planar faces for sketching as well. But sometimes it is necessary to create our own planes for sketching. So let's have a look at this example. In this view here, we have a sketch with a straight line and an arc. So we are going to use this sketch to create a sweep feature. So we will discuss sweep features shortly, but let's first talk about how we can insert a plane. So from the features tab on top of your SolidWorks window, you can go to reference geometry drop down, and in this list you can find different reference features that you can add to your model. So in this case we will be using plane, but we can also add axis or coordinate system or points. So we're going to show some of these in the next slides. But let's start with the plane. So once we click on plane, then on the left hand side, feature manager, the property manager will appear. So here we need to make some reference selection from the existing geometries. So in this case, we only have a sketch. What we are trying to do is to create a plane at the starting point of this line, and we also want that plane to be perpendicular to the line itself. So our first reference would be the line. So what we need to do, select the first reference box, then select the line. So you would see that line is already pre-selected in this example here. And then we can define different relations based on this reference selection. So we want that our plane to be perpendicular to this line. So typically SolidWorks will automatically pick up the best relation from the list. But if your model picks up any other different options in this list, just switch to the perpendicular option. So what we tell the software that we want to insert a plane which is perpendicular to this line, but it can be anywhere along this line. So we want to define its position. To do that, we need to switch to the second reference, and that would be the start point of the line. So we just carefully select the point as our secondary reference. And we want the plane to be coincident at that point. So once you have made those two selections, you will see the message to say that your plane is fully defined. And once it's fully defined, you can insert the plane, clicking the OK button. So one way of inserting a plane is using any existing sketch or faces. We can also insert a plane just parallel to one of the existing planes at certain distance. So to do that, we can effectively select the plane that we want to offset. So in this case, top plane is selected, and then we can define the offset distance from the options. So this will create another auxiliary plane parallel to the selected plane with specified distance. Okay, let's have a look at how we can insert a plane. So we have a new part started in SolidWorks. So the first thing that I'll be doing is to draw the sketch as we showed in the slide. So I'm starting from the sketch origin, then drawing a line, just moving my mouse out, similar to how we can add another line in the chain and moving back to the endpoint. You see just right next to the mouse cursor where it changed to a pencil, we have two concentric circles. So once we see that, we can move it out again, then it would start drawing a tangential arc to our endpoint of the line. So if I just move back again, so I just moved back, see that two concentric circles again. So this is how we can switch from a line to arc in more practical way. So let's do that one more time. So starting from sketch, a line, just move my mouse out slightly and back to the endpoint. Once I see the circle, then move my mouse out again, then I can draw a circle at any size. So we want to draw a half circle here. Okay. So let's set a dimension. Let's just make this 100 length and the radius is 50. So what happens here, we haven't fully defined the length of arc, so it can be at any angle of completion, or it can be a full circle. So what we are going to be doing, we are going to be selecting the center point of the arc and the end point of the arc. So once we have selected those 2 points with the Control key, then we can add a horizontal relations. So that would make it a half circle. Okay, so let's just exit the sketch and rotate it slightly. So what we want to do here, we want to add a plane to this endpoint here. So from the features, we go to reference geometry dropdown and select plane. So here we need to make a few different selections as our reference. So our first reference would be the straight line. So once we made this selection, we have options, different relation options to select. So we want our plane to be perpendicular to this line. Okay, so here is perpendicular, but it's still yellow. That means we haven't fully defined the references and constraints. So it can be anywhere along this line. But we want to locate it at the start point of the line. So this is going to be our second reference, that start point. So once we see the message fully defined, we can click OK to accept it. So now we have a plane perpendicular to this line and located at the start of the line. So the second method is basically offsetting a plane from a plane. So to do that, we can again go to reference geometry and select plane. And now we need to select an existing planar face or plane. So you can select either the standard planes from the design tree, or you can select the plane that you just created. So once you do that, you need to specify the offset distance. Okay? So if you would like to flip the offset, you can do that, or you can create a number of planes in series. So once you're happy with the inputs, you can just click OK, and that would insert a secondary plane to your model. So the second feature that we are going to be discussing today is swept boss or base feature. So in the last session, or in the first session, we talked about the main feature types in SolidWorks, and we used some of them in the first session. We talked about the extrusions, we talked about the revolves, and we also said there are two other main feature types called swept and loft. So let's start with the swept. So effectively, swept is very similar to the extrude feature, but instead of following an orthogonal extrusion direction, we can define a path. Okay, so let's have a look at this example here. So here we have a profile or of a circle, then a line and arc as our path. So we can use sweep feature to create springs, pipes, tubes, or similar type of geometries. So if you think of each of these design elements, they all have a constant cross section, but their extrusion direction is not linear. It's basically a route. So we can implement this method using the sweep feature. So effectively, a sweep feature requires a profile sketch and a path sketch. So in this case, the profile sketch is a circle, and then path sketch is a linear line and an arc. You would need to use sweep feature when you are making part 13 of your Sterling engine. So let's have a look at how we can use sweep boss base feature. So we said that we need a profile sketch here. So it is actually good practice to define your path sketch first, and then using the path sketch, create a reference plane for your profile sketch. So this is basically what we have done so far. So we're going to use this plane 1 that we created earlier to create a profile sketch. So let's do that. I pre-selected the plane and then open a sketch on this plane. So you can rotate your view normal to screen, or you can use Ctrl+8 shortcut to bring your sketch plane normal to your screen. Or you can just rotate and look at from a 3D view angle. So what we are going to be doing here is just to draw a circle from the center of the sketch plane, then dimension it to be let's say 10mm diameter. Okay, so let's close this and go back to features and select sweep boss base feature. So here we need to make two selections. The first one is profile, which is the circle that we just created. The second one is path. So it is the sketch that we created earlier. So if you just select the line on the sketch, SolidWorks should pick up the all sketch entities for that. So you can see the preview of your end model, and here you can explore different options, but for this simple example it's not going to make any difference if you change your profile twist, or you can explore different profile orientation, but the one that we want to use is follow the path. So it would always normal to the path sketch, and we don't want any twist. So once we're happy with it, we can just click OK. So here is another example of how we can use sweep feature. So typically a spring can be made using sweep boss base feature. So let's investigate the geometry. What we see here is circular or any other type of profile which is constant along a helix path. So to do that, we need to create a circular profile and a helix. SolidWorks has a command to create a helix and spiral type of geometries to make spring like models or any other geometry that may need helix shape. So to do that, we need to start with a base sketch. So it can be a circle, and which can be converted to the third dimension using the helix and spiral feature. So if you have a circular sketch like that, then you can go to curves. From the features tab, you can go to curves and helix and spiral. Then using the parameters of a helix and spiral, you can define the shape itself. And then once you define the curve, helix curve, you can use it for sweep and boss feature. So in helix and spiral, there are different parameters that can be defined. So you can use pitch and revolution. So in that case, the pitch is 7.5 and number of revolution is 10. So if you multiply this, the helix height would be 75 millimeter. Or you can control the height and revolution. So you can say, I want my helix to be at 75 millimeter height, and I want to fit 10 or any other number of revolution. So it would automatically create that shape with calculating the pitch. Or you can define the pitch and height, then the software will estimate the number of revolutions. So you can also define the start angle or the helix direction, if it's clockwise or counterclockwise. Okay, let's see how we can make a helix and use a swept boss feature to create a sprint model. So we said that we first need to start with a simple circle and then create the helix. So select the top plane and open a sketch on the top plane. Then select circle and draw a circle from the center. Let's use Smart Dimension tool to assign a diameter to the circle we just drew and let it be 100. Let's click OK and let's close the sketch. So go to features now, and from the curves select the helix and spiral and select the circle we just created. So you can use pitch, revolution and height to define your helix. In this example we will be using pitch and revolution only. So our pitch is 7.5 and the revolution is 10. We can also change the start angle. So you see how it changed the start point of the helix on the graphic area. Let's just keep it at 0. And also we can change the direction from clockwise to counterclockwise. And once we're happy with that, click OK to accept. So here is a simple helix that we are going to be using as our path for a sprint model. So the next step is to create the profile sketch. So we will be making a simple circular helix using swept boss base. We said earlier that it's good practice to create a plane for sweep profile. So let's do that. We want a plane on helix. So it's going to be perpendicular to helix. and also we want it to be at the start point of the helix. So similar to what we did with the last example, we just selected the helix itself and a point on the helix. So now we have plane for profile. Let's select the plane and then go to sketch and open a sketch here. And now we can draw a circle. Okay. If you actually pay close attention here, you would see that it doesn't actually snap in the endpoint of the helix or sketch origin. So let's draw a small circle just slightly away from the helix and the origin, and then right click on the point, and from the flyout toolbar click select others, and then let me just do that again. Let's just right click and go to select others, and then we have a point here. So in the list, just carefully select the point and then select the center point of the origin. So that might be a bit tricky to do. So if we just select these 2 points, as you see, we have no options to define a relationship between the selected points. So what we need to do here, so basically let's select the helix itself. So it may take a while to select it. Then control select the center point of the circle. So once you've selected the helix and the circle center, you would have option to add a relation between those 2 selections. And we can use Pearce relation to position it. So just be careful where it's positioned. It may snap to a different point. So I will just use Ctrl Z to bring it back. Maybe it might be a good idea to bring it closer and then select a point closer on the helix and the center point itself, and then make them piercing. So with a 5th try, you can find a way to add a Pearce relation between the helix and the circle, and use smart dimension to give a diameter, let's say 2 millimeter. Let's just zoom in to see if it's everything okay. Yeah, all looks good. And now we can close the sketch. So go into features, sweep boss base, and then select the circle as our profile and helix as our path. So just zoom out to see the preview, and again you can explore different start and end condition or different profile options. But effectively this is what we are trying to create. So once we are happy with the geometry, let's just click OK. So here is a simple spring model that we created using helix and sweep feature. You can also use helix feature to create a machine thread on a bolt model. To do that, similar to the spring, you would need to create a helix, but at this time you would have a different profile, which is your thread form, and instead of using swept boss base feature, you need to use swept cut. So you start with a stock material in the model and then cut and remove material using swept cut. Okay, now have a look at how we can use swept cut. So first we need to create the simple bolt geometry. I'll start a sketch on front plane. Let's just simply extrude a circle with 10mm diameter, so we are making a metric 10 bolt up to 50mm length, and then at this phase we will also be adding a hexagon so we will make one of the straight edges of the hexagon horizontal. Then we will define geometry. We will define a dimension across the flats of the hex. So for metric 10, that would be typically around 14 or 15 millimeter. So let's make it 15, and then extrude this up to 5mm. So here is our simple bolt model. So now we need to create a helix as our cut path. So similar to the spring example that we did earlier, we will start a sketch on this face and then draw a circle. So let's just draw it slightly bigger than or smaller than the edges of the bolt, and then holding the Control key, select the that face edge and the circle and make them co-radial. So they are now at the same diameter, so we don't need to define or input the size of the circle again. And now using the helix and spiral tool, let's define the pitch as let's make it 2, and then in this instance we will use height and pitch. So the height is going to be 40 and the pitch is going to be 2, and let's start from 0, but it's basically creating this to the wrong direction, so let's just reverse the direction to make sure that it's actually on the bolt. We can do clockwise or counterclockwise, depends if we are doing a right hand or left hand thread. So let's use clockwise in this example and click OK. So similar to what we did earlier, we could create a plane at this point, or if you actually look at carefully, the top plane is going to be the plane that we would be creating here. So no need to create a plane for this example. So let's use top plane to draw a circle. apologies, that's not going to be a circle. Effectively, let's look normal to the plane using the Control 8 shortcut. So typically threads will have triangular forms. So let's draw that triangular form. So starting from the edge of the model, and let's make a simple triangle. So you can find different thread forms or different thread profiles, but the one we are going to be doing here is basically that triangle will have all three edges equal. So let's assign equal relations with selecting the three edges and just make the width 1 millimeter. So I'm just using arbitrary numbers, not following any standard, but you can find the standard numbers looking at the different thread standard tables. Okay, so once we have done that, let's close the sketch and then go to features and select the swept boss base. So that triangular form is our profile, and then helix is our path. But I made the wrong selection here. Let me just close out this. Apologies for that. We need to select the swept cut feature, not the boss. So we are trying to cut and remove material here. And once you've selected that, you would see it's pretty much the same as swept boss base. So you need to select the profile that you want to cut and remove, and the path, that would be the helix we created earlier. Okay, and once it has processed all the data, it would show you a preview. Okay, here is the preview. I'll just zoom out slightly so that we have a clear view of what the end result would look like. And I'll click OK. And that creates a simple thread cut. But again, as I said earlier, this may not be the best way of the model and accurate 3D thread form. Okay, so all the dimensions that I used in this model are just random dimensions that I selected. In reality, you need to make sure that all your sizes and dimensions are made to ISO thread standards. Sometimes it is not practical to create 3D machine thread geometry on SolidWorks. As you could see in the previous slide, when you create a real 3D geometry of the thread, it usually produces very complex geometries. And if you think of an assembly containing a large number of components with that level of complexity, it would require significant computational power, and it may affect the model performance when you try to manipulate the view or try to edit your model. So to do that, we can simplify the thread representation using a feature or annotation in SolidWorks called cosmetic thread. So it basically provides a simple representation of a machine thread in 2D form, and when you also create a drawing from your model, SolidWorks automatically picks a cosmetic thread up and shows it in a very simple way on a 2D view. So let's see how we can use cosmetic thread. Once you've selected the cosmetic thread tool, you need to select an edge to start with. So in this case, it's going to be the end face of the cylindrical boss of this bolt. Then from these parameters, you can select different standard, different type, or different size. We will mostly be using ISO standard, and then again, mostly we will be dealing with the machine threads and the size. The software will automatically pick up the closest available size, but if that's not right, you can also select different sizes. And finally, you need to define the end condition. So whether it's a thread up to a certain length, or if it's going all the way to the end. So you can define that from this drop down here. For good practice, you initially dimension your cylinder or hole if you are using a female thread, taken from ISO metric thread tables. So let's see how we can use cosmetic thread instead of a complex 3D thread cut as we created earlier. So I will just start deleting some of these features that we created earlier. So to do that, you can just right click on the feature that you want to delete and select delete option. So as you see, my computer is already struggling to render this 3D thread form. So considering I have a number of bolts in a typical assembly, this computer would struggle quite a lot. So hence we need a much simpler form. So I will also delete the helix and spiral feature that I created earlier. And then holding the control key and selecting these two sketches, I would also delete them. Okay, so we just bring the model back to the simple bolt shape. So now we can go to Insert, Annotation, and Cosmetic Thread. Okay, so we need to select the Start Edge, and then from the standards, we will select ISO, type is machine thread, and size is metric 10. And we want our end condition to be blind. So if it's blind, it's starting from this face and ending at 40 millimeter. Okay, so once we've made all these selections, let's click OK. And basically what we see here under the, if we expand the boss extrude 1 feature, you would see that cosmetic thread is added. It doesn't show anything on the geometry, but now software knows there is a thread on this model as we defined, and when it comes to drawings, it would automatically insert that thread lines to the drawing views. And the only thing that we can see is a small circle on this end face of the bolt that's representing the minor diameter of the thread. The other advanced feature that we are going to be discussing today is loft. So we briefly talked about loft feature in the first session. We said that we could use it to blend two different profiles. And in fact, loft generally produces quite complex shapes. Loft is a very powerful tool that can be used to create organic shapes or more natural looking surfaces. So at basic level, it allows blending of multiple sketch profiles. It doesn't have to be only two different profiles. You can have a series of profiles to blend. And it's very advanced feature. We can use some guide curves to control how different profiles can be blended. So when using loft, consider the manufacturing method for a part. So organic shapes or free-form surfaces are typically harder to machine or create drawings for compared to prismatic geometries. So here is an example. So we have two different profiles here. We have a circular profile, and then we can define a plane from this end face at a certain offset distance, then create a rectangular profile on this plane. So if we look normal to the plane 1 or this end face, effectively that's what we would be seeing. So it's going to be a rectangle and a circle. So what we are going to be doing is blending these two profiles. So once we select the loft tool from the features, we can select the profiles that we want to blend. So in this case, it's going to be the edge of the cylinder and the rectangular sketch that we created. So once we made this selection, we can see the preview, how SolidWorks are blending two profiles. Something to be careful here, as you see, at each profile, you would have at least one control point. So these control points are going to be defining or controlling how your profiles can be blended. So when you are using loft, you can effectively drag and drop these control points at anywhere along the relevant sketch. So let's have a look at this example. You can simply drag and drop this point to this bottom corner. So in that case, it's going to be blending this bottom corner with that control point here on the circular profile. And similarly, you can drag this control point along this circle. So that would also change how the geometries are constructed. But if you have this setting, and the control points are given in the point similar to this view. Effectively, the end geometry would look like that. Using the simple bolt model that we created earlier, I will show you how you can use loft feature. So, as we said, loft feature blends multiple profiles. So in this example, we just want to create another profile to use loft. So using the reference plane, we will create a plane at, let's just make it 20mm offset from the bolt end face, and let's click OK and start a sketch on this plane. So using the Control 8, that would bring it normal to the screen. So let's create a simple rectangle, and let's just add smart dimensions. Let it be slightly greater than the diameter. Let's make it 15 by 7.5. Okay. And then select the bottom edge and the circle. Let's just make them tangent. So let's just fully define it. The position is not fully defined. What we can also do, we can make one of these vertical edges tangent to the bolt shank. So now it fully defines the rectangle. Let's just look at what's happening here. I will hide the plane so that it doesn't confuse us. So here is the profile, and there is the second profile that we want to blend. So let's use the loft boss base feature. First profile that we would select is the edge of the bolt, and the second one is the rectangle. So you can click on any point of your sketch. So let's just select that, and you notice that it picks up two different control points near to our selections. So we can simply drag and drop these points, and that would produce different results. So you can make it more like twisted in this way, or you can rotate the control point on the circle if you would like to do so. But once you're happy with the control points, you can click OK. Then it would create a rather complex geometry using the loft feature. Another advanced tool that we are going to be covering is shell. The shell feature simply allows you to take a solid part, as you see here, and turn it into a thin walled structure. Okay, so you can control the wall thickness. You can effectively remove the geometry in a controlled manner. So when you are using loft, you don't need to create any sketch, so you can directly apply it to any existing geometry on your model. What you need to do basically is select which face you want to remove and the wall thickness on the remaining faces. Let's start with creating a simple cube to use shell feature. So I'm starting a sketch on top plane, and using the center rectangle tool, I'm starting from the sketch origin and drawing rectangle. So that would be 100 millimeter by 100. So I'm just not adding the second dimension. So basically we can select one of the horizontal and vertical lines together and make them equal. Okay, and now we can extrude this up to 100. So here we can explore a few different things with simple boss extrusion. So we can either offset from the or extrude from the sketch plane up to a certain depth or height in this view orientation, or we can use mid-plane. So effectively what mid-plane does, keeps your sketch at the middle of the extrusion and create an extrusion with given depth. So it would be 50 millimeter upward and 50 millimeter downward. So eventually you will have 100 millimeter extrusion, but you keep the sketch plane in the middle. So this way I will keep my sketch origin in the center of the part. So let's click OK and use shell feature. So we said we don't need a sketch to use shell feature, so we can go to shell command. So here we need to define a few parameters. The first one is the thickness. So we can use 10 millimeter default thickness for this example. Second one is faces to remove. So we need to select faces that we want to remove. If we select these top faces, it will remove that face and assign 10 millimeter thickness elsewhere. Let's have a look at the preview. Okay, so that's basically what will happen. Or if you would like to move a second face, we can select that. And similarly, we can select another one to remove. Okay, it's basically what we are trying to do. So let's select those two faces and remove it. Another feature that we are going to be discussing today is Hole Wizard. It's a very useful tool inside SolidWorks that allows you to quickly create holes within a part or assembly without the need of drawing or using multiple features. So effectively we can create a hole using either cut extrude or revolve cut features. But Hole Wizard feature allows us to make this in a more controlled way and also according to certain standard hole sizes. So you don't have to predefine a sketch to use Hole Wizard. All you need to do is just go to Hole Wizard tab. Just go to Features tab and select Hole Wizard. Once you've made the selection, on the left hand side you will see the feature properties. Hole Wizard is effectively made up of two tabs. The first one is Type, that covers the creation of the hole. So here you can define different hole types, whether it's going to be a clearance hole with a countersink or counterbore, or just a simple drill, or a threaded hole. And there are a few other advanced hole types. And once you've made the hole type selection, you need to define a standard. Most of the time we'll be using ISO, and then you can define the type in that standard. Okay, whether it's a machine thread or any clearance hole or any other type. So once you have selected the standard and type, you need to define hole specifications. Again, most of the time we will be working with metric threads according to ISO. You can select different metric sizes. Then if it's a clearance hole, you can define the fitment, whether it's a normal fit or close or loose kind of fits. So based on your selections, the default or standard sizes will be generated by the software, but you can also override any of these existing parameters. Once you define the hole specs, you can define the end condition, and you can also select different options based on the hole type that you are creating. So once you have defined the type, define the parameters under the type tab, then you can switch the position, and here it will give you a graphical representation of a hole and allow you to place the hole on a plane or as a 3D sketch. So all you need to do, just select a point where you would like to drop the hole, and then define that point using sketch relations and dimensions. Okay, here we have a pre-modeled disc with 150 millimeter diameter and 30 millimeter thickness. So let's use Hole Wizard. Okay, so let's use Hole Wizard. So I'm just going to the Hole Wizard feature, and here we have type and position. So in this example, we will add a countersink hole. And then from the standards, we will select ISO, and there are different head types that we can select. So let's select the hex socket countersink head. And from the hole specifications, let's select metric 10. So that would be a normal fit, but let's see if we select close fit, the true hole diameter would be 10.5. If we select loose, it's going to be 11, normal 11 and loose 12. But we don't want to customize any of these parameters, so I'll just uncheck that. So we have different end condition here. If we select blind, we need to define a blind hole depth. Okay, so there are different depth options, or you can define a true hole. So let's make it blind with 10 millimeter depth. So here we have two options. We can define this depth up to a shoulder, or we can define this depth up to the tip. So I'll just show you how this works in a bit. Okay, and here we have different options. If we want to add any increased countersink head clearance or any added counterbore, we can do that. But for this example, we're not going to do this. And now we can switch to position. So we can select at any point on this face, and then we can drop it anywhere that we want on the face. So let's snap it to the sketch origin, which is the center of the face. So if you would like to add more holes, we can do this in a similar way, or simply hit the escape key that would stop the command. So once we click OK, it would create a blind hole. So let's see what those different end conditions are. So I will just enable this section view at right plane, and let's look normal to the cut section and see what's happening here. So I'll just right click on the feature and select edit feature. So if I define the depth up to the shoulder, it is basically where the drill diameter ends. But if I define depth to up to the tip, it is basically the tip of the drill bit. So that preview is representing a drill bit, and in a typical drill bit tip would have 118-degree angle. So you can either define it from the plane, so from the plane to the drill bit tip, or to the shoulder. So it's far common to define it up to the shoulder. So let's use that. The other option is to create a hole going all the way through. So by selecting that, it would define the end condition where the part ends. Okay, so let's use that. As you see, it creates a true hole. So earlier we looked at how we could create a plane as reference geometry in SolidWorks. We also said there are a few other different reference geometry types, so let's quickly have a look at how we can use those. So the first one we are going to be discussing is point geometry. So effectively, using the point feature, we can create a point on a defined position of our existing geometry. So when you select the point feature from the reference geometry dropdown, you can see different selection methods. Here is an example. We can define a point at the center of an arc or circle, or we can define a point at the center of a face, or a point can be intersection of two lines, and there are a few other advanced methods. So in this example, let's assume we have a simple disc-like geometry, and we want to create a point in the center. So the selection that we need to make is center of a face, and we need to select the face. The software will automatically create a point at the center of the face. And we can also use this point to define a hole position at the center. Okay, so we can use hole wizard to insert a hole to this point. Here is the first practice part of today. Last week we started to make this part as an example for advanced sketching exercise. But at this time, we will remake this part from scratch using the features that we discussed earlier in this session. So one of the tips that I can give you is basically try to keep your sketches as simple as possible. So in the last session, when we were doing this part, we tried to draw the outline of this complex geometry. But there could be different approaches that can be used. One of these would be splitting the part into the individual or simpler features or shapes. Let's have a look at this outline. So it's basically a circular outline with certain sized cutouts and then fillet radius to blend these cutouts, and all these geometry are in a pattern around the circular outline of the part. So we can instead of drawing a complex shape, we can break this down to individual features. So let's talk about part planning. Earlier in the last session, we said that so every time when we are making a part, we should plan ahead. So let's see what steps that we need to take to plan ahead. So the first step is choosing the best profile. So let's have a look at some examples and try to decide which profile that can be chosen as the best sketch profile to start with. So the first example is a circular disc with a boss base in the feature. Let's have a look at this and try to choose the best profile to start sketching when we are making this part from the scratch. So looking at the base of the part, so this can be the first geometry as our best profile. So let's have a look at another example. So here we have slightly different shape. So the side view would be the best outline of the first sketch. Here is another example. So in this case, we can select this front profile as our best profile. And another one, as you can see, it's a simple extrusion. So this is going to be our best profile for this part. And the last one, so we can choose a few different one here, but so what we see from the top is going to be the best outline profile to start with. After choosing the best profile, the next step is to choose sketch plane. As we said earlier, we have three main sketch planes in every part. So we have front plane, top plane, and right plane. So it would make a difference at the end result of your part, which sketch plane you start sketching from as your first sketch. So let's have a look at this example. So if you choose your best profile as your as the base of this part, so basically your part orientation would be different if you choose top plane or front plane or right plane as your sketch plane to start with. And the final step is looking at the details of the part. So let's have a look at this example here. Effectively, this part has two main bosses. So once we have identified the main features on the part, then we can choose the best profile which is going to be the outline of the base geometry. And then this is going to be the bottom face of our part, so it would make sense to select the top plane to start sketching or placing our best profile sketch. And then all we need to do just to create these main bosses on the part. So the first is the base feature. So using the best profile on choosing sketch plane. It's going to be a simple extrusion up to a thickness. Then we have this side boss. It can be a lug or any other geometry. So once you have created those two, the rest is just the details of a part. So the next step would be adding the cuts or holes, and finally fillets or chamfers, or in more generic terms, the dress-up features. So here we have a refresher practice tasks. So these are effectively the parts that you had in the first session slides. So in the first session, we asked them to create these parts using a simple sketch or features. But at this time, you can recreate these parts using the advanced features or different part planning techniques. So once you look at this part, you can try to understand or try to determine which profile would be best to start with and how you can locate that profile in the three main planes, and then how you can break these parts down to individual features, how you can use advanced features, and how you can complete your parts with the other fine details. And similarly, you can apply all these techniques to the original parts that were given in the first slide. And this is the last two parts that you can use. Here is we have another practice task. So here we have a relatively complex, or at least a slightly more complex part than we have dealt with so far. So in this part, you need to follow all the planning steps that we discussed earlier. You need to think how you can choose your best profile, how you can locate your best profile in your SolidWorks planes, and how you can break this down to individual features. Okay, so typically the modeling of this part should take around 15 to 20 minutes of your time. If it takes longer, that means you need to practice your SolidWorks skills. Please revisit the practice parts in the previous slides, try to make them, and then come back here and try to remake this part again. Here we have another task for you to complete. So this task is about planning part modeling. Again, you need to use all the planning strategies that we discussed earlier, and you should also think about the design intent. Okay, so when you are making your part, you should be careful about how you create your features, and you should make your part so that if you'd like to modify your part in the future, it can easily be modified. So any change that might be made later should be captured in design intent. So we will look at the part first, try to understand how we can model it up, and then we'll make it in SolidWorks. Then you need to save this part, and we are going to use this part when we are making assembly examples in the third session. So here is the valve body. Let's try to read this technical drawing. So if you haven't seen a drawing at this level yet, don't worry about it. We are going to be covering the details of technical drawings and how you can create a drawing at this level. But effectively, let's try to understand some basics about the drawings. So what we see here, three main views of your part. So here is what we see from the front. Then in this view is what we see from the top. So if you look the top of this part, that's effectively what you would be seeing. And if you look from the side, in this case, if you look from the left side of this part, and this is effectively what you would be seeing. We also have a section plane. Again, we are going to be discussing the sectioning and any other detailed view creation in technical drawings in the coming sessions. But effectively, the section plane, the section view cuts your part and shows the internal details of your geometry. Okay, and then there is a detail view, which is a zoomed view into this circled area. Okay, so effectively, what we need to do, we need to think about a few things. So the first thing that we can say about this plane is, well, the first thing that we need to determine whether that part has a plane of symmetry or not. So let's look at the top view. So this cut line here, effectively, if you look at carefully, we would see that this line is actually representing a line of symmetry for this outline. So if we think that in 3D way, that would be a plane of symmetry. And if we ignore all these internal details, so let's ignore all these holes and any other thread features, etc. And we would also not be seeing this hole and that one. We can also talk about another plane of symmetry. So that is going to be a vertical center plane of this part in these two views. Okay. So the third one is going to be a horizontal line on those two views. So we can talk about three planes of symmetry if we ignore all the internal features. If we take the internal features into account, we can still talk about one plane of symmetry here, and one plane of symmetry is just representing this vertical line. Okay, so considering the symmetry conditions of this part, it would make sense to locate the origin at the center of this part, where all three planes of symmetry are intersecting. So we can use our three main planes as our symmetry planes, and the intersection of those planes is basically the part origin is going to be the center of this part. And we have some more practice parts that you need to complete in your own time. So these are all required with the parts we also gave you in the first session and told you to save them and bring to the third session for assembly practice. So here is we have more parts to complete. So please save all these parts and bring them to the third session for assembly practice. So here is we have ceiling adapter, and then an adapter part, a valve body, adjuster screw, a control wheel, control rod, a washer, control screw. So here is the list of the parts that you need to complete. Please save them with these names and just bring to the next session for assembly practice. So let's talk about the material properties in SolidWorks and how we can apply a material to our SolidWorks part models. So effectively, we can apply stock materials to parts in SolidWorks very easily. All we need to do is just configure the material option on the feature manager design tree. So all we need to do, just right click on the material line on the design tree and select edit material, and you would see a default SolidWorks material library where you can select some predefined materials, or if you would like to create a custom materials, you can use that tool to do that. Something that you need to be careful when you are creating a custom material, you need to ensure that your material specifications and material properties are correct. So once you have applied a material to a SolidWorks model, then you can review the mass properties of your model. So effectively, once a material assigned to a part, a material comes with a density, basically it applies a density to your solid volume. Then SolidWorks can estimate mass, volume, surface area, center of mass, and moment of inertia of your geometry. So using the material properties, now we can start discussing how you can make a flywheel. But before that, let's define what a flywheel is. So effectively, a flywheel is a rotating mechanical device that's used to store rotational energy. Flywheels have a significant moment of inertia, and those resist changes in rotational speed. So flywheels typically have quite a high moment of inertia, and we said earlier that we can get moment of inertia of our geometry from SolidWorks if we have material applied. So effectively, a flywheel stores energy, and the amount of energy stored in a flywheel is proportional to the square of its rotational speed. So here is the formula for amount of energy stored in a flywheel. So the two parameters that we need is rotational speed and the moment of inertia. So the rotational speed is basically a system parameter. So if you would like to increase the energy stored in the flywheel, we should increase the moment of inertia in this equation. So how we can increase the moment of inertia? It's basically adding mass to your geometry at a greater radius from the axis of rotation. So we will look at how we can use these parameters in SolidWorks. So here we have another example practice task. So what we need to do here, you need to design a simple flywheel. You can start by creating a thin disc with 100 millimeter outer diameter and 10 millimeter thickness, and then create a hole through the center of the disc with 10 millimeter. Then apply material as alloy steel. Then go to mass properties and write down the mass and moment of inertia around the center axis, which would be axis of rotation of your component. So now using the various features that we discussed earlier, try to experiment with various ways of reducing the mass and increasing the moment of inertia by systematically removing material from the disc. So the initial geometry that we created is our design space. Then we will start removing material with observing the mass and the change in the moment of inertia. And let's see how we can reduce the mass, and for a given mass, how we can increase the moment of inertia. So this is a free design exercise, and there is no definite answer to this question. So you need to come up with your own design features and try to explore different mass and moment of inertia values with different features. Something to also bear in mind. So when you're designing a part, you should always consider manufacturing methods, whether you're going to be make your part with casting, or it's going to be a fully machined part, or it's going to be 3D printed. So different manufacturing method will require different design techniques and different features to use. Okay, now let's make a simple flywheel geometry and see how we can apply materials. So let's start a sketch on front plane, and then a circle with 100 millimeter diameter. So let's just do that, and then extrude it to 10 millimeter thickness. And we said on the front face we will have a hole with let's just change it to simple drill size, and then 10 millimeter hole. So wherever possible, try to use hole wizard instead of extrude cut or revolve cut feature. So if you have a hole, it's good practice to use that. Okay. So the end condition is going to be true all, and the position is going to be in the center. Okay. So here is the design space of the flywheel. So here in the design tree we have a material saying not specified. Let's just right click on that and go to edit materials, and here we have SolidWorks predefined material library. So you can find different material types and different grades under each category. The material that we are going to be using in this task is alloy steel. So let's select the alloy steel, and as you see, there are different material properties, the elastic modulus, Poisson's ratio. These are going to be needed in the second semester when we are doing stress simulations. But the one that we need here is mass density. So once we apply alloy steel to this part, we are applying all these properties. Okay, so I'll slightly move this window so that we can see the model. So once we apply material, notice how the material appearance is also applied to the model. So as you see, now it more looks like steel. So let's close that. And now we can start looking at different material properties. To do that, we would need to go to Evaluate tab and then go to Mass Properties. So it's showing the mass properties of our component, so the part 5. So density is 0.01 grams per cubic millimeter. But we also have options here to override the units. So if you'd like to use kilograms per let's say meter cube with 3 decimal, let's click OK. As you see, now we have more accurate results here. All the changes you make here is only applied at mass properties, so in your model is still working with millimeter, gram and second units. So let's just change these options to the default settings. Notice it's using different value here. It's only because of an error on the number of decimals that we have. The value is actually correct. So when you change it to a different unit, you will see that the number of decimals may change. Okay, so the mass is nearly 600 grams, and the center, the axis of rotation is z-axis. If you actually look at this coordinate system showing the center of mass of our component, you would see that the z-axis is our axis of rotation. So we need to look at the moments of inertia values for z-axis. So here are those two values. Okay, so whichever the one you look, it wouldn't make difference for this particular case. So the first one is showing the moments of inertia taken at the center of mass and aligned with the output coordinate system. So here is the center of mass and aligned with the output coordinate system. And this one is just taken at the output coordinate system. And effectively, these are the same, but they could be different if we didn't make the center of this part at the part origin. Okay, so when we look at these values, let's just note this down. So it's 755,870. Okay, so let's take a note of this and let's see what happens if we cut and remove any geometry. So let's start a sketch on a face of the part, and then let's just bring it to the normal. So what I'm going to do, I will draw a circle with 15mm diameter, and let's use central line to make that circle circle center aligned vertically with the origin. Okay, and then using the smart dimension, let's add a dimension to that line. So basically that circle is positioned 15mm from the center. And then I would use extrude cut. Let's just cut this all the way through. Okay, so obviously we removed some material, and we would expect to reduce the mass, and also using the circular pattern tool, let's just copy this feature with circular pattern around the center. So use equal spacing and add 4 circles. Okay, so let's see what happened to the moments of inertia. So let's go to mass properties. So the mass obviously has reduced. We have a slight reduction also in moments of inertia. So we have around 755 grams square millimeter, and now that reduced down to 742,000, obviously. So what I'm going to be doing, I'll keep the mass constant. So I'm not gonna change anything or not gonna add any other cut feature. So let's just note this down. It's 544.28 grams. Okay. So let's go to the cut extrude feature and edit this sketch and increase this length to 25. And then let's see what happens in the mass properties. Okay, so now the moment of inertia is 720. But we kept the mass constant. Effectively, we have the same cutouts, but at different pitch circle diameter. And let's just change this again, and now make it 35 at this time. And check the mass properties. And here is the moment of inertia is below 700, so it's at 687,000. So for a given mass, we can see how we can control, how we can increase or decrease the moments of inertia. So if I remove material from larger diameter, we decrease the moments of inertia. If we remove from closer to the center, we will have greater mass moments of inertia. So using this technique, you can control the mass and moments of inertia to design a certain flywheel. As we said in the first session, at the end of each video, I would recommend you to watch some my SolidWorks videos I hope you all have access to my SolidWorks portal now. If you can't access, please review the CAD and CAE discussion forum on the Moodle, and there are some instructions there how you can sign up and activate your subscription. So after completing the exercises from today's session, if you are struggling to understand any of the subjects that we discussed, you can watch these videos in my SolidWorks. Additionally, I also added some videos about different sketch tools that we didn't discuss in the first session. So these are tools that you may not need to make any of the parts, but that may help you to modify your sketch easily. So the first one is showing how you can trim your sketch entities, how you can use mirror tool, and how you can convert or offset sketch entities. So these three are completely optional. Those are just extra skills that may help you to practically create complex sketches. But the other tools about part modeling, so this is the topics we discuss, so planes, points or axis, sweeps, how you can make a helical spring, lofting, shell, hole wizard, different pattern features. So these are the advanced features we discussed in this session. And there are some design intent videos, so how you can use design intent for part orientation, how you can use design intent for different end condition for the features, and then a demo for how to approach building a model in SolidWorks. And final two videos is about how to apply material properties and how to use measure and mass property tools in SolidWorks. And finally, there are some step-by-step interactive tutorials that you can complete to solidify the subjects that we discussed today. So if you go to SolidWorks welcome screen and learn tab, then click on the tutorials, switch to basic techniques, and then the first four ones, fillets, revolves and sweeps, pattern features, and lofts. So you can complete those four tutorials to understand how and why each button is clicked when we are dealing with those features. So we discussed all the learning objectives as we mentioned at the beginning of the session. So we talked about the planes, sweep boss, cosmetic thread, loft and shell features, different reference features, how hole wizard can be used, what steps that you need to take when you are planning complex parts, how you can apply material to SolidWorks bodies to determine solid body properties, and how you can design a flywheel. So now you have skills to make all parts that you need to make for Stirling engine that you need to submit at the end of the semester. So please try to model these parts as soon as you can, so that you have time to remake all this part. So now we can conclude our video and session here. So hope you find this session valuable and you learned about these features. If you have any question about how to use any of these features, you can always send a message on CAD and CAE discussion forum, or you can just send me an email. Thank you very much. Bye bye.